Imagine you're standing on a construction site. Heavy equipment is moving in, soil is about to be graded, utility trenches are scheduled to be installed, and right in the middle of that site stands a mature oak that the developer wants to preserve. At that moment, your role as an arborist becomes critical. Tree preservation during development is one of the most complex responsibilities arborists face. It requires knowledge of tree biology, soil science, risk assessment, and construction practices. And for the BCMA exam, understanding how to properly protect trees during site development is essential. In this podcast, we're going to explore the systems and strategies arborists use to protect trees when construction and trees must coexist. Tree preservation is about much more than putting up a fence around a tree. Successful preservation requires planning, documentation, soil management, and careful coordination with engineers, contractors, and municipal regulations. In this podcast, we'll explore how arborists assess trees before construction, how protection zones are established, how soil and roots are protected, and how arborists guide construction teams through practices that reduce damage. We'll also discuss planning tools like a tree inventory and management plan, along with regulatory tools such as a tree ordinance and tree preservation order. And as we move through these concepts, think about how each one affects the long-term stability and survival of a tree in a developed landscape. Tree preservation always begins with understanding the existing tree population on a site. Before any development work begins, arborists often conduct a tree inventory. This is a systematic record of trees on a site, including species, condition, location, and measurements. One of the most important measurements recorded in a tree inventory is diameter at breast height, or DBH. DBH is the standard measurement of trunk diameter taken at 4.5 feet above ground level. DBH is more than just a measurement. It often determines tree value, preservation priority, and the size of protection zones required during construction. Once trees are inventoried, arborists evaluate their condition through tree risk assessment. This process identifies structural defects, decay, root damage, and site conditions that may increase the likelihood of failure. From there, arborists develop a tree risk management approach that determines whether trees should be preserved, monitored, pruned, or removed. For trees selected for preservation, the next step is planning. A management plan is typically created to outline how trees will be protected during construction. This plan includes protective measures, construction restrictions, monitoring requirements, and detailed specifications that contractors must follow. These specifications may include fencing requirements, excavation limits, soil protection practices, and irrigation plans. This level of planning is essential because trees are extremely vulnerable to construction damage. One of the most important concepts arborists must understand during preservation planning is the critical root zone, often abbreviated CRZ. The critical root zone is the area surrounding the tree that contains the most important roots for water uptake, nutrient absorption, and stability. A common method for estimating this zone is the trunk diameter method. This approach multiplies the tree's trunk diameter to determine the radius of the protection area. While methods vary by guideline, the principle is consistent. Larger trees require larger protection zones. Another visual reference arborists often consider is the dripline. The dripline represents the outermost spread of the canopy, where rainfall naturally drips from the leaves to the soil. Although roots often extend well beyond the dripline, it provides a useful visual reference during site planning. The protection area established around a tree is called the Tree Protection Zone, or TPZ. To enforce this zone on a construction site, arborists require installation of a Tree Protection Zone barrier, often abbreviated TPZB. These barriers are typically sturdy fencing systems that prevent equipment, materials, and foot traffic from entering the protected root area. This is a critical step. Without physical barriers, protection zones often become compacted or disturbed during construction. And that leads us to one of the most common causes of tree decline during development: soil compaction. When heavy machinery drives over soil, the pore spaces between soil particles collapse. This increases soil bulk density, often abbreviated SBD. As soil bulk density increases, oxygen availability decreases, water infiltration slows, and root growth becomes restricted. In other words, compacted soil suffocates roots. For trees that must remain in high-traffic areas, engineers sometimes design systems like suspended pavement. Suspended pavement uses structural cells beneath sidewalks or pavement to support loads, while allowing uncompacted soil for root growth below. Another strategy used in urban design is the tree island. A tree island is an open soil area within paved environments, such as parking lots, where trees can grow with less soil restriction. But even tree islands can become compacted over time if they are undersized or poorly managed. In some construction scenarios, arborists must also deal with changes to soil grade. Grading is the process of raising or lowering the ground surface during development. This can be extremely damaging to trees because roots require stable soil conditions. If soil is added around a trunk, it can bury the root flare and create conditions for decay. In some cases, a structure called a tree well is installed to keep added soil away from the trunk. A tree well creates a retaining wall around the trunk, allowing grade changes outside the structure while maintaining the original soil level around the tree. However, tree wells can create other challenges, such as poor drainage or restricted gas exchange, so they must be designed carefully. Another common construction practice that threatens trees is trenching. Trenching involves digging long, narrow excavations for utilities like water, gas, or electrical lines. Unfortunately, trenching can sever large numbers of roots, especially if it occurs within the critical root zone. To reduce this damage, arborists may recommend tunneling instead. Tunneling installs utilities beneath root systems, without cutting through them. In some cases, careful root pruning may be necessary before construction excavation. Proper root pruning creates clean cuts that reduce the risk of tearing and decay compared to random root damage from excavation equipment. When root systems must be exposed during preservation work, arborists sometimes use an air excavation device. Air excavation uses compressed air to remove soil without cutting roots. This allows arborists to locate structural roots, evaluate root health, and perform careful work around sensitive root systems. Structural roots are the large woody roots near the base of the tree that provide anchorage and stability. Protecting these roots is especially important for maintaining tree stability after construction. Soil conditions also play a major role in tree preservation success. The texture and structure of soil affect how well roots grow and function. An ideal soil for many trees is loam, which contains a balanced mixture of sand, silt, and clay. In urban environments where soils have been heavily disturbed, arborists may recommend a soil amendment to improve soil structure, drainage, or nutrient content. Monitoring soil moisture is another important part of preservation. One tool used by arborists is a tensiometer. The tensiometer measures soil moisture tension, which indicates how hard tree roots must work to extract water from the soil. This information can help guide irrigation decisions during construction, when soil conditions and root systems may already be stressed. Another factor arborists consider is the water table. The water table is the level below which soil is saturated with groundwater. Construction activities that alter drainage patterns or raise the water table can lead to root suffocation in species that require well-drained soils. Imagine you're consulting on a commercial development site with several mature maples. The developer wants to preserve the trees along the street frontage. During your tree inventory, you measure DBH, evaluate structure through tree risk assessment, and designate tree protection zones. You specify installation of tree protection zone barriers before any equipment enters the site. Later during construction, the contractor proposes trenching a utility line directly through the protection zone. At this point, your expertise becomes critical. You recommend tunneling beneath the roots instead of trenching, and you supervise limited root pruning where necessary. You also monitor soil conditions with a tensiometer and specify mulch and soil amendments in areas where compaction occurred. These actions greatly increase the likelihood that those maples will survive construction. For arborists, recognizing construction damage often comes down to connecting symptoms with past site disturbance. Reduced live crown ratio, often abbreviated LCR, can indicate chronic stress caused by root damage or soil compaction. Live crown ratio represents the proportion of the tree's total height that contains living foliage. A declining LCR often signals that the tree has lost vigor. An arborist investigating this decline might discover increased soil bulk density, root loss from trenching, or altered drainage affecting the water table. Understanding how construction practices influence tree biology allows arborists to diagnose problems that may not appear until years later. For the BCMA exam, you should be comfortable distinguishing between related protection concepts. For example, understanding the difference between the critical root zone and the tree protection zone is important. The CRZ describes the biologically important root area. The TPZ is the designated construction protection area established around the tree. Exam questions may also test your knowledge of how soil compaction increases soil bulk density and restricts root function. These connections are foundational to tree preservation practices. Let's connect the major ideas from this chapter. Tree preservation begins with assessment tools like a tree inventory, DBH measurement, and tree risk assessment. From there, arborists develop a management plan with clear specifications for protecting trees during development. Protection focuses on preserving the critical root zone through a designated tree protection zone enforced with a tree protection zone barrier. Arborists must also manage construction activities like grading, trenching, tunneling, and root pruning. Soil conditions are equally important. Soil compaction increases soil bulk density and reduces root function, while systems like suspended pavement and properly designed tree islands can help preserve rooting space. Tools such as air excavation devices and tensiometers allow arborists to work carefully around roots and monitor soil conditions. Tree preservation represents one of the most important roles arborists play in modern landscapes. As cities expand and development continues, the ability to balance construction with conservation becomes increasingly valuable. Municipal regulations such as a tree ordinance or a tree preservation order often require arborists to guide preservation practices and ensure compliance. Organizations like the Sustainable Sites Initiative, often abbreviated SSI, also promote development practices that protect soil, water, and urban tree canopy. At its core, tree preservation is about conservation. It's about protecting the long-term health and stability of trees while allowing responsible development. For BCMA candidates, mastering these concepts prepares you not only for the exam, but for real-world leadership in urban forestry and arboriculture. And throughout your career, you'll find that the arborists who understand construction impacts and preservation strategies are often the ones who make the biggest difference in protecting our urban forests. As we wrap up this series, it's worth stepping back and looking at the bigger picture of what arboriculture really represents. Throughout these chapters, we've explored a wide range of topics, from the biological foundations of how trees grow, to the soil systems that support them, to the many environmental stresses they face in urban landscapes. We've looked at pests and diseases, diagnostic processes, planting practices, pruning techniques, and the tools arborists use to support tree structure and improve soil health. We've also explored how arborists evaluate risk, assign value to trees, manage safety on job sites, and work within the broader context of urban forestry and tree preservation. Each of these topics represents a different piece of the profession, but in practice, they are never isolated. Every decision an arborist makes requires integrating knowledge from multiple areas at once. A pruning decision depends on tree biology, structural mechanics, site conditions, and long-term management goals. A risk assessment requires understanding defects, load dynamics, site targets, and mitigation options. A soil treatment plan depends on soil science, root physiology, and the environmental conditions surrounding the tree. Professional arboriculture is not simply about performing tasks on trees. It is about understanding living systems and making informed decisions that support tree health, longevity, and safety within the landscapes people live in every day. One of the most important lessons throughout this series is that trees exist within complex environments. Urban soils are compacted. Water availability is inconsistent. Construction alters root zones. Infrastructure competes for space. Trees respond to all of these pressures over decades. And the work of arborists is to interpret those responses and guide management decisions that balance biological needs with practical constraints. Arboriculture therefore requires both technical knowledge and professional judgment. It requires the ability to observe carefully, diagnose accurately, and recommend management strategies that are appropriate for the species, the site, and the long-term goals for the tree. For those preparing for professional certification or advanced credentials, the material covered in this series represents many of the core knowledge areas expected of experienced arborists. But certification is only one milestone. Arboriculture is a field that continually evolves as research expands our understanding of tree biology, soil ecology, and urban forest management. The most effective arborists remain students of their profession. They continue learning, observing, and refining their practices over the course of their careers. Ultimately, the work of arboriculture is about stewardship. Trees provide shade, habitat, stormwater management, air quality benefits, and aesthetic value to the communities where people live and work. Proper management allows those benefits to persist for generations. Whether you are climbing trees, consulting with clients, managing urban forests, or studying for professional exams, the goal remains the same: to care for trees in a way that respects both their biology and their role in the human environment. Thank you for taking the time to work through this series. And as you continue your work in arboriculture, remember that every tree tells a story, one written in growth rings, root systems, and structural form. The role of the arborist is to learn how to read that story and help guide its next chapter. You've been listening to the Arborist-podcast. Our goal is to grow our collective knowledge, one domain at a time, and we're glad you're here for it. If you enjoyed this podcast, please like, share, and subscribe to help us keep this momentum. Until next time, let's keep growing this community together.